Today we're going to talk about solving a homogeneous system of linear differential equations with constant coefficients. This is the general form of such a system. Here we have n differential equations and n unknown functions, x1 through xn, those are the unknown functions. And we can write that system as a single matrix system, x prime of t equals ax of t, where here, of course, our vector function x of t is just x1, x2 through xn. These are all functions of t. And our matrix A is what we'll call the coefficient matrix, a11, a12 through a1n. All the way to an1, an2 to ann. So with these as our x and our a, this system of homogeneous linear constant coefficient differential equations becomes x prime of t is ax of t. And the question is, how in the world are we going to find these functions x1 through xn that make this system work? Well, based on the earlier stuff we did, there's a reasonable guess. And so I'll just show you that guess. The guess is that if lambda is an eigenvalue for the matrix A with corresponding eigenvector v, then one solution to the differential equation is this vector x of t equals e to the lambda t times v. So let me be clear, if v, the vector v, is the vector v1, v2 through vn, then by this I mean that your solution vector x of t, which again is the vector x1 of t through xn of t, would just be e to the lambda t times the vector v, which is exactly this vector e to the lambda t v1 through e to the lambda t vn. So why in the world would this work? Well, the computation is almost trivial. For this choice of x, we can certainly differentiate and find x prime of t, the derivative of the vector function x, which is just the entry-wise derivative at each position. You'll notice when you take the derivative of each position, you just end up multiplying by lambda. You get lambda e to the lambda t times v, which is just lambda x. And of course, if lambda is an eigenvector, if v is an eigenvector for A with eigenvalue lambda, then ax will just be A times e to the lambda t v. E to the lambda t is just this constant. It's a function of t, but it can be pulled out of in front of the vector multiplication. It's scalar. As far as our vector space, it's a scalar function of t. So this is just e to the lambda t av. And because v is an eigenvector, this is just lambda. Av is just lambda v, and we're multiplying that by, let me rewrite that, just lambda e to the lambda t times v, which is just lambda x. So if x is e to the lambda t times v, x prime is this, ax is this, which is the exact same thing, and thus this is a real solution. I'll just put a check here. That solution works. Now that tells you one solution. Now, what did we see last time in the video lecture and earlier in chapter 7? We saw that in general we can expect to find n independent solutions. Those will constitute a fundamental set of solutions. Well, this tells us if we have a single eigenvector v with corresponding eigenvalue lambda, we'll get a single solution, and by a single solution, I mean a single solution vector x that will tell you a value for x1, x2, up to xn. How will we get others? Well, there might be other eigenvectors. Of course, any multiple of v is an eigenvector, but if we just take a multiple of v, we'll get a solution vector when we take either lambda t times v, which is just a scalar multiple of the solution we already had. It won't give us an independent solution. It is possible, when you have a single eigenvalue, that there are more than one independent eigenvectors with that same eigenvalue. And if you just take different independent eigenvectors, you'll get different solutions for that same eigenvalue. And of course, if you take a different eigenvalue, say omega is a different eigenvalue for a, not equal to lambda, and you look at the vector w, one of its eigenvectors, a nice theorem in linear algebra says eigenvectors corresponding to different eigenvalues are linearly independent, and you'll get a new independent solution. Since we know we need n solutions in the end to have a fundamental set, if we have, as an example, n distinct eigenvalues, each will have its corresponding eigenvector. This set of the n eigenvectors that we get this way will have to be independent, and we'll have n independent solutions. We'll have a fundamental set of solutions, and we'll know all the solutions. That would be the nicest case. We'll see, however, things aren't always quite so simple.